Let us see what is okay, dear student. Let us see what is there in this question. What is correct about the nature and the range of strong interaction between the nuclear particles? So the question is about the nuclear forces, and we are not considering weak forces. It is attractive at all the particle separations. It is attractive at all particle separations. It is attractive for the particle separation between zero point 0.7 fermi and 3 fermi. It is repulsive for the particle separation greater than 3 fermi. No, it is repulsive at all the particle separations. Not at all. So, my dear students, in this question, they are literally talking about the nuclear forces which are present between proton and neutron, and the other way. So, this nuclear force is basically charge independent, and this is a strong nuclear force, and so it is acting between all of the nucleons. But there is a catch here. Like there is a bit of information I think that you must not be having. So the graph of this goes somewhat like this. I'm not able to draw it properly. Okay. So like let us say this is the force and this is the separation between two protons or two neutrons. So the graph moves somewhat like this somewhat. Okay, obviously I'm drawing with my hand, so it's not that particular. So this is the point. See, here for this much of the region the force is negative, and for this much of the region the force becomes positive. So point number one about the nuclear forces is that they are short range. So beyond 3 fermi meter, 3 fermi means that 3 into 10 raised to power negative 15 meters, it ceases to exist. Like at this point, you can clearly see that it is actually becoming an asymptote nearly zero. So this is like 3 fermi meter. So at 3 fermi meter, it becomes zero. So obviously your range starts with 3 fermi meter. Negative force always refer to the attractive force. So this is attractive force. So always remember, attractive forces are always negative. One of the example, the best example is electromagnetic interaction. So you talk about a positron and electron. So the Coulombic force is given by K. So E plus is positron multiplied by E minus divided by R square. Clearly, this is having the negative charge. This is having positive. So the product of that will be giving you a negative force. So overall, it is negative, and they would be attracting each other. So I've just proved you that a positive charge and a negative charge, they are attracting each other because the force, because of the formula also, it is coming out to be negative. Okay, having said that, now this is the point, like it is nearly zero point 0.7 fermi meter or like zero point 0.8 fermi meter in our Indian books, like the Indian board CBSE. Our book says that it is nearly zero point 0.8 fermi meter when the force actually becomes zero. It's like there is this proton and there is another proton, so they have an equilibrium position. It's not like they're always attracting, and they have a certain distance. That distance has to be maintained just like a spring. So this distance, when the equilibrium is there, equilibrium means that the net force now will be equal to zero. That distance is zero point 0.8 fermi meter or zero point 0.7 fermi meter. So zero point 0.7, this point to 3 fermi meter, it is attractive. So it is attractive between zero point 0.7 and 3 fermi meter, absolutely correct. And if it is lesser than that, now if you are separating these two particles, so they will attract each other. That is why you cannot break the nucleus. Like it's not that very easy to break it. So if you create a gap between two protons, they will try to attract each other. And if we try to push them and we try to reduce the distance between two neutrons, two protons, or one proton and one neutron, then they start repelling each other just like spring. So the force becomes a positive. Positive force means repulsion. Positive force means repulsion. So repulsion is taking place at this point. It means yes, repulse, it will be repulsive at some times, but it is not like the distance greater than 3 Fermi meter, wrong. But it is repulsive for the distance lesser than 0.7 Fermi meter. It becomes repulsive. So C is wrong. D says that it is repulsive every time. No. A says it is attractive all the time. No. Hence, the answer will be B for this question. And let us see what is the answer given in the mark scheme. Clearly, the answer is B. It is attractive between the distance of 0.8 Fermi meter here. So this graph is negative here. Yeah, this from this point to this point. This is the explanation for this question, my dear students. This is Professor Varun. Thanks for watching the video. Please subscribe to the YouTube channel for even more interesting videos. Okay, then. So all the best. Bye.